All right, so today's tutorial is going to be about assignment 2, which, as you should all know by now, is about neural machine translation using transformers. I'm going to start with a little intro. I'm Julia. You might have seen me answering a lot of the questions on Piazza. I'm a PhD student at U of T. My background is in computer science and linguistics, and I did undergrad at U of T as well. And my research here is on value alignment in large language models. So the idea with, what value alignment is the idea that language models and technology in general inherently encodes a particular set of values, and that can be sometimes show up in, for example, implicit word choices. So a lot of what my research is on language reform and the values that large language models communicate in word choices around gender and gender-inclusive language. So if you guys are, any of you are undergrads looking to do research, I'm always looking for people to work with. And if people are doing like other socially oriented research or just want to talk about research and are in grad school, I'm also always excited to meet people in the department. Some non-work things about me: I like camping, and I have a dog named Sophie. So this is a photo from a backpacking trip I went on this summer, and a photo of my dog. So nice to meet you all. Okay, so some context for thinking about this assignment, and this is sort of an icebreaker question that I like to do at the beginning of tutorial classes, especially when I'm first meeting a group of students, to try and get people to engage a little bit. So recent breakthroughs have greatly improved machine translation. I think I made this slide in 2022 for a previous version of this assignment before ChatGPT was something that people, you can ask it to translate things for you now, and that's actually one of the things that you'll be doing for the analysis portion of the assignment. But a question, if I could see a show of hands, who remembers the first time that they used translation software? Yeah, and who doesn't remember the first time? Yeah, way more hands. So I feel like each year I ask this question, more and more students answer that they don't remember. For me, the bottom one there, it's from a Mac OS widget from the 2000s, and I played with it a lot as a kid, translating things back and forth until it was just nonsense. But yeah, so thanks for participating in this icebreaker. Okay, so the outline for the rest of the lecture today, it's going to pretty closely follow the structure of the assignment handout, so talking through the different parts of the assignment that you'll be implementing, and at the end I'll also talk about the analysis portion and what you're expected to do for that. And I'll conclude with, there'll probably be some time left at the end, so I'll let you guys go a little bit early perhaps, but I'll stay around for an office hours style Q&A where people can come ask more questions about the assignment. And as you probably know, most of the material that is relevant for this assignment is covered in the NMT and Transformers lectures, so that's where you'll get a lot of the theoretical information that's important for being able to do this assignment. But what I'm presenting today is mostly the sort of the bridging between that technical knowledge and what you need to do to be able to do the assignment. And that's particularly relevant this year, where we've created a new version of the assignment. So to give a little bit of context, behind the scenes context about how that worked this year, another PhD student, TA Arvi, did the work of updating the assignment from the previous version, which was RNNs with attention, to the current version, which is Transformers. And so that he used all his TA hours doing that, and then my part is the delivery, and also keeping track of places where there might be mistakes in the assignment and correcting those as well. So I really appreciate people participating on the Piazza and identifying issues, even for ones that are maybe smaller things that we haven't been able to address right away, will definitely benefit students in future years. So thank you very much for your participation and patience. Okay. And so the big picture of what this assignment is doing, it's translation using the Canadian Hansard's data set. This is, I guess, I keep this slide in partly because I think it's funny. Someone made it, I don't know who, from ages and ages ago. And this is a very old picture of Sean, who is one of the instructors. So now you know what he looks like a few years ago. Yeah, so the data is the Canadian Hansard's data set, translating English and French. And this points to where it's located on Teach. And the general structure of the assignment and what I'm going to be talking through today is sort of outlined here. There's a lot of detail on this slide. I'm not expecting you to be able to look at it and know exactly what's going on right away. The reason I include this is partly as a resource for you guys to go back and look at later, and also because it sort of highlights the way that the different parts of the assignment relate to each other, which is how I'm going to structure it. So I'm going to go through, we have first this sort of innermost, I guess, kind of like the core of the onion. We have these building block classes, layer, norm, feed forward layer. These are the transformer building blocks. That's in part one. And then on top of this, you have the pieces that put the architecture together. So you have these different classes, the encoder layer and the encoder, the decoder layer and the decoder, and then the model that puts it all together into a transformer encoder decoder translation model. And so that's the second part. And then the third part is the pieces for doing decoding. So it's not just having the model that can do one step of decoding, but how do we generate translations based on these inputs. So that's what part 3 is about. And then the final part, part 4, is about using this model to run experiments and also evaluate the quality of the translations. So this gives sort of a sketch of what we're going to talk through today and also what you will be doing in the assignment. And we're going to start with talking about the transformer building blocks. So the first building block that you're going to be doing is layer norm. And the only method that you need to implement here is this forward method. And what this does is it normalizes the layers distribution so that it has a 0 mean and a standard deviation of 1. And the goal of doing this is to remove uninformative variation in the layers features. So this is a pretty, I guess, almost like a straightforward, it's intended to be like a straightforward warm-up in sort of getting comfortable with working in PyTorch and on the assignment. Okay, the next one is another one that probably should be fairly familiar or comfortable if you've taken neural networks courses in the past. This one, again, you're just implementing the forward method, and it's a simple, fully connected neural network layer, and we've sort of specified each of the pieces here that you need to do. One thing that I saw on the Piazza that someone had asked about this was there's no bias parameter in the implementation, or there's no bias attribute that's initialized. And the reason is because in the linear layer module that you're using to implement this, the bias is used automatically, so you don't need to explicitly tell it to do something with bias, so if you're wondering about that. Okay, and the next layer is the one that we expect to be a little bit more, or the next module that you'll be implementing is the one that we expect to be a little bit more challenging for students. So the class is multi-head attention, and it handles both self-attention and cross-attention. The kind of big picture theory underlying how attention works has been talked through pretty in detail in the courses that Raid has taught. That's my understanding anyway. So I'm going to focus mostly on the specifics that you need to know to implement this here. So the two methods that we're implementing are the attention method and the forward method. And within the attention method, we provided in the assignment handout the formula for what you should do when there's just one attention head. But you'll note that this is a multi-headed attention class that you'll be implementing, so it's your job to think through sort of how to implement that for multiple heads. And one tip that I have for you in going through doing this process would be to think about what should be the shapes at each step if you're implementing it for a single head, and then thinking about how you would generalize that to the multi-head case. And then there's some resources linked here. So there's the Transformers lecture slides, and I tried to point to the specific slides that might be relevant, especially for thinking about the shapes. And then I also linked to a really useful illustrated transformer article. If you're struggling with attention and feel like it's confusing, I would highly recommend reading that. That's a great article. And the other method you need to implement is the forward method. And in this, you need to, I guess the main things you need to do in implementing that are determining whether it's self-attention or cross-attention, and then appropriately calling the attention method. And one thing that might be a little tricky here is some of the reshaping. So I pointed to a couple of PyTorch methods that if you're not super familiar with PyTorch, these pointers might be helpful. And if you are familiar with PyTorch, then you can just not worry about it. Okay, so that's for the multi-head attention. And that kind of concludes talking about the transformer building blocks. And next I'm going to talk about putting the architecture together. So this is where we use the different building blocks that we've just talked about to put together each of the encoder and decoder pieces, and then finally the full transformer model. So the transformer encoder layer, we've presented in the assignment handout diagrams for what the different components of this are. I think the actual implementations of these methods will look probably pretty simple. The main piece is just making sure that you understand what the different steps are and whether you're whether you're using the different building blocks correctly here. So this particular method isn't meant to be super challenging to implement. And the two relevant methods that you're going to be implementing for this class are the pre-layer norm forward and the post-layer norm forward. So we have two different versions to play around with layer normalization. And this, I guess, is also to sort of help you get a little bit comfortable in implementing things in some different ways. But again, this isn't meant to be a super challenging method. Do you have a question? Yes, so mapping, so just to repeat the question, because this is also being recorded for people online, and in case other people didn't hear, you're saying that in implementing this, a challenge that you were encountering was feeling like this diagram didn't map perfectly onto what had been shown in the other slides?
Yeah, it was just not intuitive how, for example, the skip connections were drawn.
I see, okay. To repeat, they're saying that was maybe not super clear how the skip connections were working. So yeah, if you have specific questions about that you think might be sort of unclear, I would definitely, I've been trying really hard to answer as many of the Piazza questions as I can, and that can be a useful resource, especially since a lot of students aren't here. And I guess, do you feel like you understand it now after having worked through it more, or are you still feeling confused?
So I think I understand how to implement it. It's just I think the implementation is fairly easy.
Yeah.
But I think what is not obvious is for example why do you place them from each beginning to each you know what I mean, why are they drawn there not in other places the arrows or the pluses and how would they connect? If I didn't have this diagram, how would I have gone from the paper to this?
Oh, I see. I actually am not exactly sure. Do you mean because there's equations in the paper? I'm assuming. So how to jump from that to this, or?
Well, yeah, I just didn't. Again, this diagram, I didn't see it in the paper, so I don't know where this came from. If I hadn't been given the paper, I would have never known this.
Oh, I see. Okay, so yes. I can see how that might be confusing, and the sort of step of being able to bridge from what might be in the paper to this, I can see how that might be perhaps unintuitive, but that's part of why we, I guess, provided this in the assignment handout, was to try and make that as clear as possible. And if you think the drawings of the skip connections are confusing, I'd be happy to touch base about that maybe after the in the Q&A period. Okay, so that sums up for the transformer encoder layer. And now we're going to talk about the transformer decoder layer. I won't spend too much time on this because it's pretty similar. The main difference is that instead of doing just self-attention, now here you're doing self-attention and cross-attention. And again, there are the two versions, pre-layer norm and post-layer norm. Cool. And then the transformer encoder is implemented for you. So you just need to implement the transformer decoder, so how you go through the different decoder layers to create the decoder. And the only method you need to, or I think, yeah, the only method you need to implement here, I think, is the forward method. And this should look very similar to the forward method for the transformer encoder class. So you can pretty closely parallel how that is written there. The main thing that you need to remember in implementing this is that you need to use the logic projection module that should be initialized there to get the final output. And that final output represents a probability distribution over the vocabulary, indicating what words are the most probable continuations in each position. So this is something that I think, so the question I put in there is like, what is the output shape for this method? This is something that I think might trip up students in thinking about how to use the decoder in other places. So what it outputs has, it's for each batch, for each sentence, it has predictions for each of the tokens, for each of the positions, what the next word should be. So if you're doing generation, for example, and you're predicting one word at a time, you'll need to call this multiple times, sort of adding on to the sentence as you go. And you'll need to think about what positions to extract the relevant next tokens from this generated sequence. So I'll come back to this idea a little bit when talking about the like how we put things together, especially in talking about decoding. But this is something to like maybe be thinking about. Okay, and then the last class for putting things together is the transformer encoder decoder. Some of the methods you need to implement here, or I think, yeah, all of the main methods you need to implement here as part of this part 2, we're putting everything together to get these classes, are the masking methods. There have been a lot of questions about these on the Piazza that I've been trying to answer as much as I can. And one thing that has been a common theme that I think students have been struggling with is what the masks correspond to, how they're going to be used in computing attention. So the masks are specific to the text that they are masking. So the pad mask is specific to the source text, and the causal mask is specific to the target text. And this has to do with the goals that the masks are accomplishing. So for the pad mask, the goal is that we don't want to consider any of the positions after the source text ends. We only want to consider the relevant tokens that we're generating a translation for. So that's for the pad mask. For the causal mask, which looks kind of like this, so it's like an upper triangular matrix, the purpose of the causal mask is in generation, we want to have each token only depend on the preceding tokens. So that's what the goal of the causal mask is. So that maintains, I guess, another way of putting that is it maintains the autoregressive property. And I listed the output shapes here because this has been a source of confusion for some students and also for me in going through the assignment for the first time tracing through and trying to figure out what's going on, is why don't the shapes for these pad masks, for these two types of masks, exactly match the mask shape in the multi-head attention methods. And the reason for that has to do with broadcasting rules in PyTorch. So if an index is, two dimensions are broadcastable, they can be compatible if they are the same or if one of them is 1. And that means that it allows us to not create a pad mask that duplicates for every single one of the query sequence dimensions, we don't need to do that. Or similarly for the causal mask, that doesn't depend on the individual translations. Each of them are going to have the same mask, so we don't need to have it different for each of the items in the batch. So this is, that's why we can have ones in these positions in these masks. Okay, so that is for the transformer encoder decoder. And now we'll move on to the next part, which is greedy and beam search. So this is how we use the transformer encoder decoder model to do generation. So the first way that we do generation is greedy decoding. And you'll have learned about this probably in the lectures. The intuition here is that at each step of generation, you pick the most probable word. So you pick so you just go through and iteratively pick the best one, and you'll end up with one translation. But a problem with that is that sometimes when we use a greedy strategy, we won't actually find the translation that's going to be the best if we had considered possibly some variations earlier on in the generation process. So that's going to be what we're going to talk about in the next decoding method, which is beam search. But first, to talk about the greedy decoder here. So until each sentence in the batch has a finished translation, you generate a new token. And a question that I put in here, which sort of points back to what I had mentioned before in talking about the decoder output shape, is what part of the decoder output do you need to use? So remember that the decoder output has the shape of the batch size, the number of sentences, and then for each sentence it has the the batch size. For each sentence it has the number of tokens in the sentence, and then for each token it has the vocabulary size. So you want something that has a distribution over the vocabulary size, but just for the final position that you are predicting, because that's the one where a new word is being added. So that's a hint about how to sort of use the output of the decoder to accomplish what this greedy decode method is asking you to do. And I pointed to some methods that should be useful to you, that you should use in implementing this method. Okay, that's for greedy decode. And then for beam search, you implement 5 different helper methods. So you're not implementing all of beam search, you're just implementing several pieces of it. And the first method that you implement of the 5 is initialize beams for beam search. This is probably one of the more involved. I think I would say, because it can be useful to know what to expect, I think this one is probably one of the more involved beam search methods, and then many of the others are sort of smaller helper functions. But this first one, it takes the first decoder step and uses the top k outputs to initialize the beams. So this is what I was talking about before when I was saying that instead of just generating the most probable sequence, it's going to generate k possible sequences, and at each step it says, okay, we have k sentences we're looking at. What are the best continuations of those k? Then let's score them, and then keep k of those. And one thing that I saw as a question on Piazza for this that I think is relevant is that the instructions don't say you need to use the encoder, but if you're going to be getting the decoder outputs, the decoder requires inputs that come from the encoder to do this. So you will need to call the encoder here. And as a tip, I would highly recommend looking at how the encoder is used in the decode greedy method, because it's going to look pretty similar. Okay. The next method is expand encoder for beam search. So this is a helper method called at the end of the previous method. And the goal of this is to expand the source embeddings to have a shape that is batch size times k as the first dimension instead of just batch size. And the reason that it does this is that it will more closely parallel the shape of the the decoder beams, which lets us do things in parallel. So if we have k possible translations for a given piece of source information, then we need to have k copies of that as the sort of encoder output. And a relevant PyTorch method to consider here is the expand method. Okay, I'm going to go fairly quickly through the rest of the beam search helper methods. This next one is also a sort of expand and reshape method. So here the expand part adds a expand dimension, and this lets us get the best, I guess it lets us get n equals expand completions for each of the current k translations. So this is the step where for each of the k that we're keeping track of, we look at possible, this is how many possible additional possible completions, next steps that we consider for each of the k. And then once later, we're going to cut that down. So that's why we expand. And then we reshape. So we make it so that instead of batch size times k as the first dimension, it's just batch size and then k times expand. And the reason that we do that is so that we can select the best k per batch from this pool of k times expand possible sentences that we've now created. And again, a relevant PyTorch method to use here is expand. The next one is pad and score sequence for beam search. So the one thing that I noticed in going through and preparing for this tutorial is that the padding here is actually not necessary. You can still do it, but doing it will have no effect. So in future versions of this assignment, we're just going to call this score sequence for beam search. It's useful to think for a second about the reason why the padding will have no effect. I think that helps give some intuitions for what's happening in the beam search decode method. So in the beam search decode method, on each step, it checks whether a translation has completed. And a translation is completed if it ends with the end of sentence token. And then it removes those from the set that are being passed through this generation process. So that means that all of the sentences that have been completed when they're being passed to this method have just been completed. So they have this end of sequence token, and we don't need to go through and do what the padding would do, which is add padding tokens after the end of sequence token. So that's left over from an earlier version that RV had been working on and implementing, but we don't need it anymore, so you don't need to implement it. But you definitely need to do the scoring step, which scores each of the sentences by summing the log probabilities. So this is sort of at the core of what beam search is trying to do, where it's looking at all of the, it's trying to rank the different possible sentences and pick the best ones. So you're getting the scores for that. And then the very last method is finalizing the beams for the beam search. So why do we need to finalize them? Well, I mentioned before that at each step, we remove the sentences that have been completed. But what that means is that the translations aren't all going to have the same number of tokens. So we have lots of different translations that have different lengths. So that's what you're addressing in this finalize beams for beam search method. It pads the generated sequences so that they're all the same length. So what you're going to need to do is figure out which sentence is longest and then pad all the other sentences so they have the same length, and you can return a tensor that has that appropriate shape. Okay, so that should wrap up for the beam search helper methods. And that leaves just this very last piece on model training and testing. So there are kind of two main pieces that we're going to talk through here. There is ones related to the blue score, which is how you evaluate the quality of your translations. And then there are others that are more related to training and running the model. Okay, so I'm going to talk about the blue score piece first. So we're going to be working through an example of what each of the methods or functions that you're implementing for blue scores should return for this very tiny toy example. And yeah, I think these sentences are kind of funny, which is why I kept them in. I think a TA, it's part of, I guess, the 401 lore. A TA from years ago picked these sentences, and now we're still using them, which I think is kind of fun. Okay, so as sort of with what I've been trying to do throughout the assignment in general, this is kind of trying to tie the theory that you've learned in the course. So you've learned like this is how blue score works, tying that to the specific implementation that you're doing for the assignment. So the first thing that you're going to do is implement this grouper method. So if you pass in the reference here to this grouper function, friendship is magic, then it should return friendship is and is magic because we asked for 2 grams. That's the second parameter here is 2. So that's for grouper. Now once we've done that to both of the once we've done that to both of the sentences, we can compute the n-gram precision, which is the proportion of the n-grams in the reference that are in the candidate. So, you divide by the proportion that are in the reference that are in the candidate. So you have C over N, and the details of this are in the course materials, but for this case it would be half, because half of these, the friendship is n-gram is in the reference, but is witchcraft is not in the reference. The next one is the brevity penalty. So what this does is it's intended to penalize translations that are very, very short, but in this case they have the same length, so it's just a multiplier of 1, so no penalty is applied. And then the last one is the blue score function that puts it all together. And in this case, we were looking at the blue 2 score. So it has the 0.5 times 2/3, which is the 2 gram times the 1 gram n-gram precisions. So this is, I guess, the general gist for calculating blue scores. And then one thing that came up on Piazza that I wanted to flag for people is that there is no capping, so we're not, this applies to the n-gram precision. We're not saying, oh, it can only occur, if a piece of the translation only occurs, in the candidate only occurs once, in the reference you can only count it once or something like that. We're not applying capping. And in this specific application, we also only have 1 reference in candidate per translation pair that we're looking at. So we're not doing anything that looks at a group of candidates, for example, or a group of references. Okay, all right, so that should sum up for blue score, and now we're going to talk about the training loop. So there are some methods to implement here that I'm going to talk through fairly quickly. I think for these ones, the instructions are pretty spelled out in the doc strings. So one of the methods is train for epoch, and this goes through the training process for a single epoch, as it would sound. I would encourage you to follow the instructions in the doc string here, and if you're looking for an easy progress bar, TQDM, I would recommend using that. The next method is train input target split. So this one I think might be a little bit confusing for people as to why this is necessary. So I'm going to spend a minute talking about that. So what this does is it splits the target tokens into the decoder inputs and expected outputs for each of the sentences. So because we're doing teacher forcing, we're saying this is the right answer for each position. So it's not like in generation when we're going through one at a time and being like, okay, this is what we've generated so far, this is what we generate next. This is the sort of magic that lets us train transformers really, really quickly, is that we can, in one sort of pass, say like, this is our string from start of sentence to like right before the end of the sentence. Now let's predict from right after start of sentence to the end of sentence tokens. So that's the, I guess, gist of what this is doing. And there are some questions about the specifics of why you reshape in the ways that you do for the target that were on Piazza that I answered yesterday that might be useful to people if you're feeling kind of confused about like what's going on with the shapes here. And then this one is fairly straightforward. I think we included this partly to get you guys to be just, to have this sort of literacy if you haven't done a lot with PyTorch before about like, oh, there's an optimizer that I need to step and then I need to zero a gradient and like, what are those things? But this is very like, I think this method should have like 3 lines that correspond exactly to these 3 steps, and the methods that you use to do them have the same names as how they're described here. But basically, like, the goal for this is like, do you know what a scheduler is? Well, the goal of a scheduler is to help you like know how to adjust the learning rate throughout the training process. That's like why we included this. This shouldn't be a tricky method. And then, I think this is the last one. Yeah, the last one is compute total batch blue, which computes the blue score for a batch of sentences. And a tip here that I think might trip students up that you should be careful about is not to pass the start of sequence, end of sequence, and pad tokens to this function. Okay, so that sums up for what you'll be implementing for the training loop. I'm going to talk very briefly about how to run stuff on teach.cs. I haven't seen a ton of questions about this, so my thinking is that students are not having too much trouble, but if you are, please come talk to me and I can talk to you about like how do you use SSH and like what's going on here. One thing that might be, or I guess 2 things I want to highlight that might be useful to you if you haven't done a lot of like programming or like running models on remote servers before are, I think screen is super useful as a utility. So it lets you, if you start a screen, you can run something on that and then like disconnect from the server and come back to it and still have the results there. I don't think this is super important for this assignment because the full model training takes like 7 minutes or something. So, I mean, and assuming that the server's not super overloaded, but I guess if it was overloaded in particular, the screen would be very useful. And then another thing that you might want to know about is you can check the current queue by using this sq command. Okay. So that should sum up about running things on teach.cs. I'm going to talk a little bit about the analysis part. I think this was pretty spelled out in the assignment handout, but just to give you like a sense of what this might include if you haven't like really carefully read through it yet, you're going to be translating 8 sentences from English to French using the model you train, but also 2 other models. So for the model you train, there's a cool like translate demo mode that basically opens like a Python shell where you can type in translate and then in the string the sentence that you want it to translate, and then it will return the translated sentence. So you just do that for the 8 sentences, and then you're also going to look at 2 other kinds of models. One of them is a fine-tuned, pre-trained transformer model. So these are the 2 options, and they're linked to in the handout. And I think they both, I know at least one of them and probably both of them have like a web interface that you can use for inputs and outputs. So it's not like you need to be downloading a model and running it on the server, which was my worry when I first read the assignment. I was like, are we making students do that? That seems like it would be an unfun surprise at the end of the handout. But no, there's a way to do that on a web interface. And then the last one is using a large established model. So I think this one is perhaps one of the more interesting parts of the assignment is just to be able to compare, like, if you train a model in 7 minutes on a GPU for an assignment, how close is that to like a state-of-the-art transformer model that's seen so much more data? So that is, I think the questions, the meat of that part of the assignment involve kind of qualitatively comparing like what kinds of mistakes are they making? Is there sort of some in-domain, like are the models that are trained on the Hansard's data better at translating like Canadian legal, like parliamentary setting sentences than GPT, just because it's seen that kind of data? These are the kinds of things we want you to be thinking about and engaging with in this part of the assignment. Sick. Okay, and then, so I think that wraps up for everything that I have prepared. For the rest of the sort of 9 minutes I think left, I'll be around here at the front to answer any lingering questions that you might have, or if you just want to say hi. But yes, thank you all very much for coming, and good luck on the assignment.